Hello everyone, welcome back to Applied Engineering channel. Today we are diving into part 3 of our Cycle DHX series. If you are new here, hit that subscribe button and turn on notifications so you don't miss out HVAC&R insights. This video is all about past, present and future of HVAC refrigerants. We will compare their performance using NIST Cycle DHX simulation software, and we will break down key metrics like global warming potential, ASHRAE safety classification, and simulation results for things like COP, mass flow rates, and more. By the end, you will know which ones are fading out and which are set to dominate in 2025 and beyond. So let's get started. Alright, let's kick things off with an introduction to Cycle DHX. This is a powerful NIST developed tool for simulating vapor compression cycles in HVAC and refrigeration systems. It handles single component refrigerants and blends, factoring in thermodynamic and transport properties, perfect for engineers and researchers like us. In this series, we have already covered what Cycle DHX and its key features, how to download and install it, and running it in different modes like reference, impose, and simulate modes. If you missed that, please watch my previous videos of Cycle DHX Part 1 and Part 2. Now we will also dive into practical examples to show you how to use it hands-on. So why is this software awesome? It gives semi-theoretical simulations that help predict real-world performance, making it ideal for comparing refrigerants under fixed conditions. So stick around because we will use it to analyze our lineup of past, present, and future refrigerants. In the past, we have R22 and R134A. These were the workhorses, but they are high GWP offenders contributing to ozone depletion and global warming. Present day options include R410A as the baseline, along with transitional ones like R32 and R152A. R410A has been standard, but as of 2025 regulations are tightening, new US equipment cannot use it anymore due to its high GWP value of 2088. Looking to the future, we are shifting to ultra low GWP like R290, that is propane, R1234YF, and R454B. These are eco-friendly but often come with flammability trade-offs as per ASHRAE safety groups. This shift is driven by global agreements like Kigali Amendment and US AIM Act phasing down high GWP HFCs. In 2025, we expect more adoption of A to L classified refrigerants like R1234YF and R454B for their balance of performance and lower environmental impact. So next we will see how these stack up in simulations. Moving on to the heart of our analysis, that is the simulation inputs and outputs using Cycle DHX. We set a fixed cooling load of 7 kW that is roughly equivalent to a 2-ton air conditioning unit, a common residential size. All refrigerants were tested under identical conditions, that is same heat transfer fluid temperatures at the evaporator and condenser, and fixed configuration for those components. This ensures a fair apple-to-apple comparison. The software spits out key outputs like compressor work, compressor suction, volumetric flow rate, mass flow rate, COP of cooling, and COP of heating. These metrics helps us evaluate efficiency, system size, and costs. In the next slides, we will explain what each means and dive into the simulation. So from here, we will now move to our simulation software and we will see how to use it for all these refrigerants. So This is cycle THX 2.0 version. First we will go to the file and we will open the already examples inside the software. Here you can see a file with the name AC test. So we'll just click it and we will open this file. As we will open this file, you will see it has loaded this file. And what we can see, it has already selected the refrigerant R152A. In the cycle options, it has already selected a single stage cycle without including liquid line and suction line heat exchangers. And in the cycle specification, we can see it has selected the impose mode and it has selected heat exchanger representation with delta T value. What else we can see, that it has also given the values of heat transfer fluid temperature inlet values and temperature outlet values for both evaporators and condenser, along with the delta T value, that is the temperature difference between the secondary heat transfer fluid, that is air, and the refrigerant. It is important to note that this delta T is the average temperature difference between the secondary fluid and the refrigerants. Also, it has defined the saturation temperature drop because it has selected the saturation temperature drop in the options. Also, it has provided the superheat and the subcool value of 5 degrees Celsius. It has also selected the heat exchanger type configuration of cross flow. So what we will do, we will just check on the established reference parameter, and here you will see it will give you all the tube inner diameters, tube length, number of tubes per circuit, and a number of circuits. It will already calculate the heat transfer area on the refrigerant side for the evaporator and the condenser. By clicking on the established reference parameters, it will evaluate the reference parameter for our first run, and based on this reference run, it will then evaluate the properties of other refrigerants and with other conditions. So now what we will do, we will first run it into the impose mode and we will impose all these geometry parameters in the simulation, and we will evaluate the reference parameters. We will click the run simulation button and it will run it for R152A. And here you can see it has run it for R152A in the impose mode and it has evaluated the reference parameters. What we will do next is that we will change from the impose mode to the simulate mode, and now you can see it has grayed out some of the options which we cannot change now. So what it has done, it has actually imposed the geometry of the heat exchangers and few other things like the delta T and saturation temperature drop values, which we cannot change now. But in the simulate mode, what we can change is that we can change the secondary fluid inlet and outlet temperatures, we can change the superheat and subcooling values, and we can also put yes for optimization of the number of circuits, which will optimize the number of circuits and will improve the COP value. Also, along with that, we can also change the compressor isentropic efficiency values, volumetric efficiency values, and electric motor efficiency values. We can also switch compressor from this isentropic efficiency mode to switch to map mode. And we can select any of the map available inside the software. But now we will just stick to the example which is already provided, so we will switch it to the efficiency mode. Also, we can see it has a cooling capacity of 7 kilowatt, which we can also change in the simulation mode. And here you can see the vapor lines pressure drop and the auxiliary powers. So now what we will do, we will click run simulation and it will simulate this for R152A. So here you can see the result summary file for R152A. So So here we can see what are the results. It has calculated the thermodynamic cycle results, it has calculated the compressor and system results, and it has also calculated the heat exchanger results. So here we can see the compressor and system results. So this is the compressor power, which is 0.857 kilowatt, and the COP of the system in cooling mode is 8.168, and the COP of the system in heating mode, that is 9.168, and here is the compressor suction volume flow rate, that is 8.735 meter cube per hour. So these are the four main parameters which we will compare in our simulation. Also in the heat exchanger results, you can see it has calculated the refrigerant mass flux, the delta T value, overall heat transfer coefficient value, and the refrigerant side thermal resistance and saturation pressure drop values. We will save these results, and we will save it with the name of R152A air conditioner. I have already saved this file. So what we will do next, we will run it for different refrigerants as per our presentation. So we will just go to the refrigerant, and then we will go to the single compound fluid, and then we will select our next refrigerant. Let's say it is R22. So we will now select R22 and we'll click OK, and then we will directly go to the cycle specification, and then we will run the simulate mode, because we are not changing the heat transfer fluid temperature or any other parameter, because we want to compare this refrigerant on the similar conditions. Now we will just simulate it, and here you can see we get the results for R22. From here we will again copy the values of compressor power, COP values, and compressor suction volume flow rate values, and then at the end we will make a comparison table. So now coming back to our presentation, and after the simulation run, now we will see what these parameters actually represent. So let's break down these simulation outputs one by one, and they are crucial for understanding why some of these refrigerants outperforms others. So first is the compressor power. Compressor power represents the electrical power consumed by the compressor, the system's main energy user. Lower power directly cuts operating cost, that is the electricity bills, and improves the overall energy efficiency, making the system more attractive for energy conscious markets. The second is the compressor suction volume. This indicates the volume of refrigerant vapor the compressor must handle at the suction inlet. Lower values allows for smaller, cheaper compressors, reducing system size, weight, and cost, ideal for compact applications like residential air conditioners. Whereas high volumes necessitates larger compressors, raising manufacturing and maintenance expenses. So it ties into system design. Mismatched volumes can cause inefficiencies or failures, so it's critical for scalability and retrofit compatibility. Next is the mass flow rate. This is the rate at which the refrigerant circulates through the systems to achieve the desired cooling and heating capacity. Lower rates mean smaller piping valves, reducing material cost, system weight, and installation complexity. High rates increase pressure drop, requiring larger components and potentially higher energy losses. In design, it affects heat exchanger sizing. Optimizing it lowers manufacturing cost but must align with capacity needs to avoid inefficiencies. The last but not the least is the coefficient of performance cooling and coefficient of performance heating. COP measures efficiency output, cooling or heating, divided by the input energy. Higher COP means better performance per unit of electricity, lowering running costs and environmental footprint. COP cooling is vital for air conditioning while COP heating matters for heat pumps. Its importance is that it directly impacts energy savings and system ratings. Low COP increases operational expenses and may not meet efficiency standards, affecting marketability. In design, optimizing COP can justify higher initial cost through long-term savings. Here it is the refrigerant comparison table from our cycle THX simulation. We have got ERA, GWP, ASHRAE safety group, mass flow rate, compressor power, suction volume, COP cooling and COP heating. R410A is our present baseline. So starting with the past, R22 has a high GWP of 1810 and it is A1 safe. It has a high mass flow and less compressor power. It has a moderate volumetric flow rate and good COPs. R134A has similar story of high GWP value of 1430 and A1 safety category. It has a higher mass flow rate, less power consumption and high volumetric flow rates, and it also has good COP values. Both these past refrigerants have good efficiency but they are environmentally outdated. For the present refrigerants in use, the baseline R410A has high GWP value of 2088 and it is A1 safety category. It has a high mass flow rate and it has a highest compressor power consumption of 0.893, whereas it has the lowest compressor volumetric flow rate, good for the compactness, and the least COP values. Then comes R152A. R152A has low GWP value of 124 and it is A2 category flammable. It has low mass flow rate, lowest power consumption and highest volumetric flow rate, but also it has the highest COP values. So its compressor size also will be the biggest, but all features are in favor of this refrigerant. Then comes R32. It has moderate GWP value of 675 and it lies in A2L category. It has low mass flow, it has moderate power consumption and lower compressor volumetric flow rate. Also it has moderate COP values. Now come for the future refrigerants. R290, that is propane, has ultra low GWP value of 3 and it is A3 category ASHRAE, that is highly flammable. It has the lowest mass flow rate, it has less compressor power consumption and a moderate compressor volumetric flow rate. Also it has good COP values. Next comes R1234YF. R1234YF has ultra low GWP value of 4 and it comes into A2L category ASHRAE safety group. It has the highest mass flow rate 0.0551 and it has moderate power consumption. It also has high compressor volumetric flow rate but the COP values are good. At last comes R454B. R454B has moderate GWP value of 466 and it comes into A2L ASHRAE safety group. It has moderate mass flow rate and moderate compressor power with low compressor volumetric flow rate values, and it also has a moderate COP values. So have you noticed the trends as compared to the baseline refrigerant R410A? The future options have lower GWPs but introduce flammability as per ASHRAE. Their efficiencies are better with comparable mass flow and vapor flow for the cost savings. A According to the American Innovation and Manufacturing Act, the AIM Act of 2020, from January 1st, 2026, refrigerants with only less than 300 GWP will be allowed to use in HVAC&R. For that case, we are only left with the three options from the future, and these are R152A, R290, and R1234YF. Out of these three, R152A has the highest efficiencies, but it is A2 category, while R1234YF also has comparable COP and is less flammable than R152A, whereas R290 is highly flammable among these and hence is least desirable. But which are the winners? Let's analyze. There is actually no one size fits all refrigerant. There is always a trade off between the GWP, ASHRAE safety, and efficiency. The future favors the low GWP or mildly flammable A2L options like R152A or R1234YF. COPs are comparable across the board from our simulation, which makes environmental impact and safety regulation as the deciders. You have to choose the refrigerant based on your application, its safety level, and its environment. Thanks for watching. If you enjoyed this breakdown of past, present, and future refrigerants with cycle DHX simulation, please like, share, and subscribe my channel if you like more videos and updates. That is the only way of supporting and motivating me. Thank you very much.